SVD stands for singular value decomposition. This is a matrix factorization that can be applied to any matrix, and it's one of the most important matrix factorizations in applications. So let's start with some motivation here. So I want to take us out of the mathematical world and enter the purely visual one. This is a picture of my wife's cat. And my wife's cat hates me, so my wife had to take this photo. And she took this photo on her phone and sent it to me. And I converted it to grayscale. And the uncompressed image on my phone takes up 723.06 kilobytes. Now, I took this image and I represented it as a matrix, and I applied what's called a compression technique using singular value decomposition. So here's what I did. This technique occurs in layers. So the first thing I did is I applied what's called n equals 500 compression. And the thing I want you to notice is that, at least from my perspective, these two images are completely indistinguishable. I certainly do not notice a difference between the uncompressed and the compressed. However, to get from the uncompressed image to this n equals 500 compression, whatever that means, I end up saving myself a little bit of disk space. And now what I'm going to do is I'm going to lower the compression. So now I'm going to take n equals 400 compression. And again, I don't know about you, but I certainly can't tell a difference between n equals 500 and n equals 400. But what's cool about this is it doesn't appear like I'm losing any quality. However, I'm lowering my disk space. So that's sort of the goal for people who care about image compression or data compression more generally. If you could take up as little disk space as possible without losing any quality, that's pretty good. Let's drop from n equals 400 to n equals 300. Again, I don't notice a difference in the image quality, and I'm still saving disk space. Let's go from 300 to 200. 300, 200. I'm not sure if I'm noticing any difference between 3 and 2, but again, I'm still saving disk space. So as far as I'm concerned, I don't care that much about the cat anyway, so I might as well send the 200 compression because the image looks the same and I'm saving disk space. Let's go from 200 to 100, 200 to 100 now. Again, from 200 to 100, I'm not noticing any differences. So it still appears like I'm retaining quality, yet I'm saving even more disk space. And I think we might be able to tell a difference when we drop from 100 to 50. So here's 100 and here's 50. Now, if we look closely, so I'm going to go back to 100, 100 down to 50. Now you can sort of start to notice the image blurring a little bit. We're saving disk space, but it definitely is evident at this point that we're losing quality. That's okay. It's still quite clear that this is a picture of a cat. So I'm losing a little bit of quality, but so what? It's still pretty clear what I'm communicating, and I'm saving disk space. Now when we go from 50 to 25, the image is blurring quite a bit, and I'm still saving disk space, but the image is quite blurred. What about 25 down to 10? Well, now the image is completely blurred, more or less. And we're saving some disk space, but it's not even completely clear that this is a picture of a cat at this point. And if we go down from n equals 10 to n equals 5, I think it's not even clear that this image is of a cat anymore. So we've saved some disk space along the way, but it's clear at some point we start losing perceptible quality, and then at some point we lose all quality. So here's a summary of that data. So we started with an uncompressed image that took up 723 kilobytes. And by applying these various layers of compression, we see that we're dropping disk space that the file takes up. But at some point, the quality becomes degraded to a point where the image is functionally useless. So that's sort of the goal in image compression. Try to save as much disk space as we can without losing quality. Okay, so that's a complicated photo. I now want to totally change perspective and think about the easiest possible scenario. The easiest possible scenario would be communicating the data of a solid image. So here we're looking at a solid red rectangle. And let's say that I wanted to fit this red rectangle on a 4K monitor. So a 4K monitor has resolution 3840 by 2160. So here, the idea is that, so I actually have these numbers switched. This should be 2160 pixels high and 3840 wide. So I'll fix that. But the idea is that if I'm communicating the data of just a solid red rectangle, I can represent this data with a matrix. And that matrix would just be a matrix full of maybe a signal telling the monitor to switch on its red light. So the data in this red rectangle is communicated, is represented by a matrix of dimensions 3840 by 2160. And the thing I want to alert everyone is that the data in this matrix could be more conveniently packaged with a matrix factorization. Why not take this 3840 by 2160 matrix and factor it as a column of ones multiplied by a row of red signals? What's the purpose in doing this? Well, if I think about the size of the original matrix, so the amount of data stored in the original matrix, this is a grid of 3840 by 2160 pieces of data that we have to keep track of. And that amount of data is can be attained by multiplying those numbers. 3840 multiplied by 2160 is like 8.2 or 8.3 million pieces of data. However, if I factor my matrix as a column of ones multiplied by a row of red signals, I actually lower the amount of data that I'm communicating, or I reduce the amount of data I'm communicating. Instead of multiplying these two numbers together, I'm now adding these two numbers together. 3840 plus 2160 is only 6,000. And the key thing here is that this is an equality. So I can communicate all of the data in this matrix by factoring, and I save a ton of space without reducing quality. So by factoring in this scenario, we compress our data without sacrificing any quality. Now, keep in mind, I'm not saying this is the most efficient thing we could do. I think in this scenario, probably the most efficient thing we could do would be to just simply communicate everything is red, the number of rows is 3840, and the number of columns is 2160. But the purpose here is to get us acquainted with this idea. We're communicating data in a matrix, and we can save the amount of space that data takes up by factoring that matrix, and we don't lose any quality in this process. Let's look at a more complicated example. So I guess before we move on, we should mention one thing about this matrix is that this matrix has rank 1. Every single row is the same, so the rank here is equal to 1. Let's look at a slightly more complicated example. Here you're looking at the image of the Swedish flag. I got the colors exactly right and the dimensions exactly right according to Wikipedia. So this is the Swedish flag, and here I'm representing the data in this flag with a matrix. So here the idea is that there are two colors in this flag, sort of this bluish color and this yellowish color. I can represent all of that data in one matrix with B's in place where there should be blue and Y's in place where there should be yellow. So here's coloring in the matrix to keep track of what piece of data it lives where. And one thing to point out here is that the data in this matrix, even though it looks like a really large matrix, is actually not that complicated. There's really only two types of rows here. There's rows on the top and on the bottom where you have blues followed by yellows followed by blues. And then there's all of these rows in the middle, which are all yellows. So what this is saying is that the rank of this matrix is equal to 2. So we can communicate the data in the Swedish flag with a rank 2 matrix. Well, now we can apply our compression idea to reduce the amount of space that this data takes up without losing any quality. However, since the rank of our matrix is 2, we need 2 terms to represent the data. The data in the matrix can be represented as a column of 1s and 0s multiplied by b's followed by y's followed by b's, this is communicating the data in the top and bottom rows of this matrix. And then we need to account for the middle rows of all yellows. We add a column of zeros and then ones and then zeros multiplied by our row of all yellows. So since the rank is 2, we need 2 terms to represent this data completely accurately. And one thing we could do if we wanted to further compress this data is we could approximate the image by dropping a term. And this is what I did in the cat photo. What I did was I took that cat photo and I originally represented it by 500 terms, and then I started dropping terms. And what we noticed is that dropping some of the terms really didn't affect the quality, but when we dropped too many of the terms, that did affect the quality. So in this case, we could approximate this image by dropping, say, this second term, but now this is no longer an equality, this is an approximation of the matrix. So this is one of the ideas, or this is one way to motivate the idea of singular value decomposition. How can we take the data in an arbitrary matrix and represent it as some sort of compressed sum, or approximate the data with a truncation of that sum? We'll see that when we learn about the rigorous details of singular value decomposition.